And we're up. We are recording. Okay, welcome back, everybody. Always good to have you. What I want to do is start off today. I want to start off by just quickly going over. And when I say quickly, I don't mean I'm going to speed through it. I just want to make sure that we're all on the same page and we all understand what's going on. Jack, Connor, I know the two of you have had differential equations, and so what you've seen is a little bit of a review, but it is in the world or in the context of circuit theory. So things are a little bit different because it is circuit theory. So just as a reminder, we said we're going to be dealing with second order differential equations, and those differential equations look like the following. X double prime plus A1 X prime plus A0 X is equal to some function of time. X is a function of time, and over here is some function of time. And so that's the differential equation that we're going to be looking at, a second order differential equation. Once we have a differential equation, there are two parts to the solution. So X, the solution, is the forced response and then the homogeneous response. It's those two, or the natural response. And so what we have to do is we have to find each of these two separately. So we're always going to start by finding the homogeneous response first. And you don't know why yet, but today we're going to reveal why you need to do this. So the very first thing we do is we find the homogeneous response. And the way we do that is we start by writing the characteristic equation. The characteristic equation comes from looking at that part right there. And all we're going to do is everywhere the variable is, we replace the variable by an S. And everywhere we have primes, we replace the number of primes. We check the number of primes and replace it by its number. So here I have X, I replace that by S. There are two primes, it's an S squared. Copy everything else down. A1, S to the first power, so we generally don't write to the first power, so I won't. And then plus A1, and then X to the zero power. X to the zero power is just 1. And then we set it equal to 0 because this is the homogeneous solution, so we're looking at the homogeneous equation. So the first thing that we do is we write that, and then we solve this equation for the two values of S. Okay, so we solve for the two values of S. And so the two values of S are determined by factoring this, S plus, and then I'm just going to call it S1. Actually, let me use a minus here rather than a plus. So S minus S1, S minus S2 is equal to 0. We can factor it that way. So therefore, the solutions are S is equal to S1 and S2. When S is equal to S1, it's 0. When S is equal to S2, it's 0. But we know S1 and S2 are going to be negative numbers. Why? Because if they're not negative numbers, what will happen is the homogeneous response, the response that comes from not putting in any input, will expand. It will increase exponentially. We will have just found a way to get energy out of nothing. So that's not going to happen. So these S's are always going to be negative. So we factor this and we get these two values of S. Then what we have to do is we have to look at, of those two values of S, what is true? So what is true of S1 and S2? So it's going to be one of the following three things. A, S1 and S2 are both real numbers, but they're not equal to each other. So we call it real and distinct. I'll write these things down again. So this is real and distinct roots. And we call this case the overdamped case, even though it doesn't make any sense. This is the overdamped case. And I mistakenly wrote critically damped on this yesterday. So that could be one situation. Second situation is S1 is equal to S2, and they are still members of the real number system. So they're still real, so they're equal to each other. We call this real and repeated roots. And this is called critically damped. And then the third case is the ugliest case, ugly just because the numbers are complex. Otherwise, it's not that bad. So it's S1 is equal to S2 complex conjugate. I want you to notice here, when S1 is equal to S2, just a note, they are the complex conjugates of each other, right? And I'll come to that in a moment. So this is complex conjugate roots. And for these roots, when we get complex conjugates, we say that here that this is the underdamped situation. And to me, this is just me alone, underdamped makes sense because I've got this sinusoid that wants to decay away, but it takes a while to decay away. So I get a decaying sinusoid. So it's easiest in the complex conjugate root case to say, well, look, if S1 is equal to S2 complex conjugate, let's just say, let's break it down into its real and imaginary parts. Let's call them alpha plus or minus J beta. Or in other words, A plus JB. So they're complex conjugates. So if S1 is alpha plus J beta, then S2 is alpha minus J beta. They both have the same alpha value, but they have opposite beta values. One's a positive, one's a negative. Okay, so I just want to go to this one as an example of this one. So S1 equals S2 equals 3. 3 is equal to 3 plus J0. And the complex conjugate of 3 plus J0 is equal to 3 minus J0, which is still 3. So in this case, these are complex conjugates. They're just not complex numbers. They're real numbers. Real numbers are part of the complex conjugate system, but they don't have an imaginary part to them. Okay, so I end up with those three cases. Depending upon which case we have, will determine the form of the homogeneous response. So the next thing we do after we have the values of S, so we go here, we get these values of S up here. From the characteristic equation, we get the values of S. And so I take those values of S, and from the values of S, we write the homogeneous solution. And that homogeneous solution will look like the following. I'll use the same notation, A, B, and C. A, so I have S1 and I have S2. They're members of the real. And S1 is not equal to S2. Just as a reminder, continue to write it. Here's the solution. X homogeneous equals K1 e to the S1t plus K2 e to the S2t. And this is true for any K1, K2. It works for all of them. Doesn't matter which one you choose, even if they're complex numbers. True for all of them. If we have situation B, S1 equals S2, and those are both elements of the real, so they're equal to each other. Let's just call, for argument's sake, let's just call it S1. They're both the same, so let's just call it S1. X homogeneous equals K1 plus K2t times e to the S1t. Again, true for any K1 and K2. And then the third situation was the following. It's S1 equals S2 conjugate. And so we said, let these be equal to alpha plus or minus J beta. So what will happen is we will have X sub H is equal to K1 sine of beta T plus K2 cosine of beta t, all of that is multiplied by e to the alpha t. And that is also true for every K1 and K2. Nobody asked this yesterday, but we know that S1 and S2 are exponentials. How mysteriously did this solution here turn into a sine and a cosine? I thought it was supposed to be exponentials. And so I can show you why they're sines and cosines if you want me to, or if you'd like me to. But if not, I'm not going to bother with that. But they are exponentials. Now, think of it this way. They're exponentials, but that term in the exponent is a complex term. And we know sines and cosines are complex exponentials. So that's how they turn into sines and cosines. Okay, temperature check right now. Arushi, for you particularly. So far, so good?
Yeah, I'm good. I got it.
Okay. So did you have any question on this yesterday, or did this clarify for you?
This helped clarify it, because
okay.
I think this is the part I was confused in.
Okay, so we can immediately get this. So let's do an example. Again, I'm making up an example on the fly. In fact, if you want to, you can make up the example. I'll let you, anybody, make up an example. Give me a differential equation. Give me this number here. Give me this number here. And for now, I'm just going to make it the homogeneous part because all we care about is the homogeneous part. Jordan, I'm calling on you first. Give me a number to put right there.
5.
5. Harushi, give me a number to put right there.
10.
Okay. So here we go. I immediately take this. S squared plus 5s plus 10 is equal to 0. This does not factor nicely. You can't see the factors. In fact, it's going to look something like this when we look at the factors. S plus 2.5 plus, and then there'll be a term here times j, etc. Don't worry about that because you don't know how to, most of you don't know how to do that. Let's solve for this. Let's factor it. So here we go. So S1 and S2 are equal to minus b plus or minus the square root of b squared. So b squared is 5 squared minus 4 times a, which is 1, times c, which is 10, all divided by 2. We'll see that this is equal to minus 5 plus and minus the square root of 25 minus 40. Square root of what, 15? 25 minus 40, the square root of 15, all over 2. So here we go. S1, 2 equals minus 5 over 2 plus or minus square root of 15 over 2 times j. This is a negative 15. Shame on me for dropping my negative sign. Square root of negative 15. So remember, square root of negative 15 equals square root of minus 1 times square root of 15. So up here, you can see there, that 2.5 is the opposite of that, and this one is going to be here. So what we have is these are our values of S. S1 and 2 are equal to this. So this is which category? Well, clearly it's this category right here. It's category C. So we're going to take that and we're going to write our solution. So X homogeneous equals K1 sine of this ugly number. I know it's ugly. It's not. It's not an ugly number. It's beautiful. Sine of that t plus K2 cosine square root of 15 over 2t all times e to this number right there, e to the minus 5/2 t. That is the solution of the homogeneous response. If you plug that into that equation, I guarantee you, if you plug it into the left-hand side, you'll get 0. You have to take that, then you have to take its derivative, then you have to take its second derivative. These derivatives are not hard, but they're klutzy. They're big, right? They're long terms. So that is the solution to the equation. So we never know just when we start with this differential equation, we don't know, there's the differential equation. We don't know which of the three categories we fit into until we go to the characteristic equation. And from the characteristic equation, we find the three roots. And then once we find the three roots, we say, well, where do those three roots fit? Are they here? Are they here? Or are they here? And depending upon which ones they are, if they're here, then this is the form of the solution. We just immediately write the form of the solution. This is straight in memory, or when you're taking an exam or a quiz, you have open book, open note. You want this somewhere where it is very easily accessible. Same with that one, and same with the last one. You just want them very easily accessible. Everybody comfortable on the homogeneous response? So yesterday we ended by looking at the forced response. And the forced response was a little bit different than the homogeneous response. And so we talked about the forced response. So that would be the third part, is looking at the forced response. And we said, this is always going to require us to take an educated guess. And then there are many steps in this part. So step one is the following. So one, take an educated guess. And that educated guess is the following. It looks like means it has the same form as, it looks like the forcing function plus all its unique derivatives. So looks like means has the same form. So when we say it has the same form, we scale with any constant. We look at what the form is. Oh, it's a cosine. Cosine. But then we scale it with any constant. So we put a constant in to each of these is what we do. We put this constant in, and what we need to do is we need to solve for each of the constants that are in our guess. So what we do is we then take the first and second derivative of our guess and substitute all three now, the guess and the two derivatives, into the original differential equation. So once we do that, we then solve for all unknown constants in the forced response guess. Solve for all of them. How many are there? I will never give you more than 4. 3 is kind of pushing it to the max. Because when you get more than 3, what happens is unless they're easy to break apart, if they're not easy to break apart, then you need to solve 4 equations and 4 unknowns, and that can get very, very, very difficult, and we don't want you to do anything like that. But certainly solving 3 equations, 3 unknowns, they're linear equations. You can use Cramer's rule. You can solve them that way. So what we're going to do is we're going to solve for all these unknown constants. Once we have them, substitute the values of the constants back into the guess for the forced response. Okay, so it's a process in which we take multiple steps. We take an educated guess, then we take the derivative of that guess and the second derivative. Then we take all three of those and we substitute them into the differential equation. Then we solve for the unknown constants that are in that guess. And once we have those constants, we plug them back in and we say, here it is. That's the forced response. So we did an easy case yesterday of looking at this. And the easiest case that we're going to get is always that f of t, the forcing function, is a constant. So let's go back and recall our differential equation looks like the following. So we're going to focus on this. We're going to look at this. That's our forcing function. And we're going to say it looks like that plus all its unique derivatives. So here we go. Second example. X double prime plus 2x prime plus 3x is equal to 33 e to the minus 2t. So here's my guess. And right now, it's the only guess that we would make. So we're going to guess that it looks like over here. My guess, well, it certainly looks like a e to the minus 2t. It is the same form. Notice I don't copy the constant over. Some constant, it is the same form. So some constant, that's why we have constants in here. Now, what's the derivative of a e to the minus 2t? Or better yet, what's the derivative of this e to the minus 2t? We know it's minus 2 e to the minus 2t. So what form does that have? It is the form e to the minus 2t with a constant out in front. Well, we already have that right there in our guess. So this derivative has the same form, so we don't need to add that in there. So our guess is only a e to the minus 2t. Awesome. That's not bad. What's the derivative of that? We're going to find the derivatives. Minus 2a e to the minus 2t. 4a e to the minus 2t. And now we're going to take these three and we're going to substitute them into the differential equation. But in this case, here's our differential equation right here. We'll slide this up. We'll leave it there so you can see the differential equation. So I'll rewrite it. X double prime plus 2x prime plus 3x is equal to 33 e to the minus 2t. Okay, so we said x double prime is 4a e to the minus 2t plus twice x prime, there's x prime, minus 2a e to the minus 2t. And then the last one was plus 3x, and there's x, a e to the minus 2t. And when I add all of those up, those should be equal to, according to the differential equation, that should be equal to 33 e to the minus 2t. So you'll notice there's an e to the minus 2t, an e to the minus 2t, an e to the minus 2t. This math always needs to work out. If it doesn't work out, there's something wrong with your guess, or there's something wrong with your math work. So what we're doing is we're matching coefficients of like terms. There's only one term here, and that term is an e to the minus 2t term. So there's only one term, but we're matching the coefficients. This coefficient must be equal to this coefficient. Well, first of all, let's add all that together. That's nothing more than 3a, because that cancels with that. So we get 3a equals 33, or a equals 11. Plug that back into the guess. Therefore, x sub f, which is equal to a e to the minus 2t, is equal to 11 e to the minus 2t. That is our solution. Okay, did you like that? How'd that one look? That one okay? Everybody follow along on that? Was everybody clear about this guess and why there's only one term in the guess? Is everybody clear about that? It's the guess plus all derivatives, but the unique derivatives all look the same. The derivative of e to the minus 2t is there's an e to the minus 2t there, so I keep getting e to the minus 2t back. So once I have one of those e to the minus 2t's, there are no other terms. Okay, if we're comfortable with that, let's try another example. Okay, in this example, I want to do two things. So I want to do this. Find the form of the homogeneous response also find the forced response. So we're going to do all of that. So let's start with the homogeneous response. Somebody tell me what the characteristic equation is.
S squared plus 4s equals 0.
Thank you, Jack. Right on the money. This one is easy to factor. Excuse me for a moment. Okay, let's put that to voicemail. Okay, so s plus 4 times s is equal to 0. Clearly, s is equal to 0, and s is equal to minus 4. Which category are we in? First, second, or third? What do you think? What category?
First.
Excellent. First, indeed. Real roots, they're real numbers, and they're not equal to each other. So that means we go to this solution. XH equals K1 e to the 0t plus K2 e to the minus 4t. What's e to the 0t?
1.
Good. Perfect. That's the form of, in this case, that's the form of the homogeneous response. Now, here's our differential equation. Now we want to make a guess at the forced response. So in order to make the guess, we have to look here. The form of this, forget this, put blinders on with the 75. Don't look at that. Put blinders on. The form of this is its cosine of 3t. So we just put an a out in front of it. A cosine of 3t. What's the derivative of the cosine of 3t?
Negative 3 sine of 3t.
Excellent. So we don't worry about the negative 3, but we know the form of it is the sine of 3t. And then we put our own constant out in front. Another constant, b. What's the derivative of the sine of 3t?
Cosine of 3t.
Excellent. And there we've got a cosine of 3t already. So once you get a repeat, then you're done. So it's just those two terms. The derivative of the cosine is the sine, but the derivative of the sine is the cosine. So now we're just going to cycle back and forth. We have all of the unique derivatives. Every other derivative is just a repeat. So this is our form. So now we're going to guess x sub f is equal to a cosine of 3t plus b sine of 3t. That's our guess. Now what do? We compute the first derivative and then the second derivative. Minus 3a sine of 3t plus 3b cosine of 3t. I'm just going to rewrite this so that the cosine is always first and the sine is always second. Oops, minus. Okay. Now, I want to take the derivative of that. That's not bad. So the 3 comes out again, and the derivative of the cosine is minus the sine, but this is going to be equal to minus 9b sine of 3t, and the derivative of the sine is the cosine, so it's going to be minus, and that 3 is going to come out again, minus 9a, and that's going to be cosine of 3t. So I'll again rewrite this in the order, minus 9a cosine 3t, just so it's easy to look at, minus 9b sine of 3t. And you should expect these numbers, 3 and 3, they're going to be the same, 9 and 9 are going to be the same, because it's the sine and the cosine both of 3t. All right, so we have this term, this term, this term, and now we're going to substitute into the differential equation. So I'm going to rewrite the differential equation for you so that you see it again. I don't know what happened, I just stole that out of there. So here's the differential equation, x double prime plus 4x prime equals 75 cosine of t. X double prime plus 4x prime equals 75 cosine of 3t. All right, let's substitute in double prime minus 9a cosine of 3t minus 9b sine of 3t. That's that term, plus 4 times x prime. X prime is this one right there. 4 times 3b cosine of 3t minus 3a sine of 3t. And there is no term for just x. Notice that this was x double prime plus 4x prime plus 0x. Note that. So there's nothing there. So all of this is just equal to 75 cosine of 3t. Now, we're going to group like terms and compare coefficients. So I'm going to all my cosine terms. So for my cosine term, I've got this one and this one. Here we go. Minus 9a plus 12b all multiplies cosine of 3t. And then I have my sine terms. And I've got this one, and I've got this one, plus minus 9b minus 12a. Don't forget, this one multiplies 4. All times sine of 3t. Now, it's not written this way on the right-hand side, but I write it this way, equals 75 cosine of 3t plus 0 sine of 3t. There are no sine of 3t terms over here. So 0 is what I should be seeing that coefficient as. And now I'm going to equate this coefficient must be equal to this coefficient. This coefficient must be equal to this one. This coefficient must be equal to this one. This coefficient must be equal to this coefficient. 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 This co So we now have two equations, two unknowns. These are two linear equations. Minus 9a plus 12b must be equal to 75. And then minus 9b minus 12a must be equal to 0. I can reduce these a bit, so let's reduce them. So first of all, I want to rewrite this so these are in this place. I want you to see it that way. And at the same time, I'm going to divide by 3. I think we can easily divide by 3. That looks like we can do that with no problem. So when I divide by 3 here, I get minus 3a plus 4b is equal to 25. Now doing the a first, minus 4a minus 3b equals 0. Now I'm going to solve these two right here. There are 1,000 ways to solve them, but I'm going to solve them using Kramer's rule. So remember that this can be written the following way. Minus 3, 4, minus 4, minus 3, a, b equals 25, 0. So solving for a, we get the following. We get a equals, I always start with the denominator because I just copy these numbers over. And then in the numerator, I'm going to replace these numbers here. They're going to go in the column of the numbers that multiply a. 25, 0, 4, minus 3. This is equal to minus 75. Minus 75 minus 0 over 9 plus 16. 9 plus 16 is 25 minus 75 divided by 25. If I did my math correctly, this is equal to minus 3. Now you have two options. One option is continue to use Kramer's rule, which I will do, or it's to substitute this into any of these equations. So you can do either one of them. I think they're both fairly easy to do. So B is equal to, in this case, it's 3 minus 4. It's 25, 0 here. And down here in the denominator, we're going to get the same 25. So this is equal to 100 divided by 25, which is equal to 4. So we use those values. We plug them in. X sub f is equal to. So this is my a value. A is the one that multiplied, what did we say? The cosine, correct? So minus 3 cosine of 3t plus 4 times sine of 3t. And I guarantee you, if you take this and you plug that into that differential equation, if you plug it in here, way back here, put it in there, I guarantee you, you will get 75 cosine of 3t. That's what will happen. All right, let's pause on that for a moment. So before we take a brief break, how do we like that?
I'm good.
You're good? Okay. Connor, you're good?
Yeah, I'm good.
Jordan, you feel pretty comfortable there?
Yeah.
Okay, one of the challenges here, Jordan, in this is we do have to know how to take derivatives. But in a moment, I'm going to show the general functions that we're dealing with. And then what we'll do is we'll write down what their derivatives are so that you'll always have them available to you, okay?
All right, yeah. No problem.
Good. Great. Arushi, we're good?
Yeah, we're good.
Okay. Who else? Do I have anybody else? Let's see who else we have out here. I think and Garrison. Garrison, good with all of that? Good. Excellent. Okay. So let's take about a 5-minute break. We'll come back. I'm going to give you the general types of forcing functions that we'll see, those f of t's. We'll see what those are. And then we have to talk about some specific case where the educated guest needs to be really educated. So let's take a break. We'll be back in 5 minutes. I'm going to put our recording on pause right now. So we're just going to pause the recording. Somebody remind me to record back. I'm going to put that here so I see it, but we'll want to make sure we turn it back on when we come back. Okay? Okay, I've picked up with the recording. Hopefully everybody's back and with us and ready to roll. So what I'd like to do is I'd like to take a look at what are the kinds of forcing functions that we're going to see and which ones are important to us. And I will tell you, there's one particular one that is really important, and we're going to spend a significant amount of time looking at that, but we're going to look at it in a different frame going forward. We're going to look at it without the differential equation, which is really interesting. So let's create a little bit of a table here. So forms of f of t and our guess for x sub f. Okay. So these are the general forms that we're going to see. Number one, we're going to see k. In other words, a constant value. We've done an example of that already. And our guess for that was, we guessed a, just guess a constant, because all of the derivatives of a constant are 0. Okay. The second one is k times t. And when we have something that looks like k times t, we're going to guess that it looks like a times t, but the derivative of t is 1. It's a constant. So we're going to guess at plus b. We don't want to go much higher than this. We could do all different powers of t, but for the most part, we'll restrict it to t squared. Okay, so this is we're going to guess here, at squared plus bt plus c. We always take it down to the constant. Notice, by the way, that this form and this last one here contains form number 1, form number 2, form number 3. Now, guess is the sum of all 3 of those. If you have any 3 of these combined on the left-hand side, your guess would be the same. Then we looked at k e to the at. Our guess is going to be a e to the at. And then the last one that I want to focus on is really important, and it's either something that looks like k cosine of at or k sine of at. And regardless of which one it is, and you can probably see this by what we just did in our example, our guess will be both of them anyway. A cosine of at. Notice the frequency A is that frequency. The frequency, that is a frequency, is the same. So it's always going to have the same frequency as whatever it is that's in the forcing function. But this one, we have to add B sine of AT. So for the most part, those are our forms. Now over here in this column, I'm going to shrink this down a little bit. And over here, I'm going to write 2 more columns. And Jordan, this will be for you particularly. It might be helpful to Masail as well. Okay, so this would be x sub f prime. This would be x sub f double prime. So when you make these guesses, you have to know their derivatives and their second derivative. 0 and 0, that one was easy. We saw that one. This one is a and 0. This one is, this derivative here is 2at plus b, that's the first derivative, and its second derivative is 2a. a e to the at. Its derivative is little a, capital A, e to the at. And its second derivative is a squared, capital A, e to the at. And on the sine and the cosine one, we just did that in this particular example with our guess. When we guessed a, so we actually had an omega and there was the value is 3. But when we put in our derivatives, we took the derivatives of each of these. So as a reminder, this derivative was minus little a, capital A, sine of AT plus little a, b cosine of AT. That's the first derivative. And the second derivative, staying on the same line, is minus a squared, capital A, cosine of AT, minus a squared, capital B, sine of AT. So there they are. Those are the forms that we'll deal with. I won't throw you any other curveballs. Now I want to remind you, you could have a combination of these. So you could have something that looked like this, for example. You could have f of t is equal to 3e to the minus 6t plus 2. Notice this one fits into category number 4, and this one fits into category number 1. So I have to use a combination. So the guess would be x of f is equal to a e to the minus 6t plus b. This tells us we should only guess a constant. This tells us we should only guess an exponential. There's the exponential, there's a constant. I'm not going to try to trick you with things like that, but they could pop up. You might see them from time to time. So I want you to know how to be able to handle those. All right, everybody good with that? So we should know what to do with regarding our guesses. We should know what the guess should look like, and then what the first derivative is and what the second derivative is, and then be able to plug those back in and solve for those constants. And you've seen that these constants are either A and B, or A, B, and C. That's all you have in these here. You could have more constants if you had this example here that I just wrote down right there. If you had that example, you could have more constants, but those constants would be easily separatable. Okay, concept. This concept is called excitation at a natural frequency. And if you think through what these words mean, you might be able to figure out what's going on. Students struggle with this concept, and I really don't know why. I'm not sure why they struggle. So I'm going to try really hard to ensure that you understand what this means and what consequently should you do different in your guess. So I would say right now, given everything we know, when this happens in a circuit, because it's the circuit that causes it to happen, not you that causes it to happen. When this happens in a circuit, it will cause our guess to be wrong. So we're making an educated guess. We're educated people, and we know our guess is going to be wrong. And I'm going to go through why we'll know it's going to be wrong. So let me tell you what it is. This occurs when we have, basically, when we have a natural frequency that is also part of the forcing function. So that's when it happens. So what we have to do when we observe this, And this is why we always want to do the homogeneous response first. When we observe this, we want to modify our guess because we know our guess is going to be wrong. So if we don't modify our guess, we know the guess is going to be wrong. And the modification, the way we describe the modification, to modify the guess, simply include a T multiplier in the appropriate place. And hopefully we'll completely understand what this means. So anytime there's something duplicated, we've seen this T multiplier already. So I'm going to show you an example of where we've seen the T multiplier already. And it was here in category 2. So when something is repeated, ready? Here's what's repeated. S1 equals S2. See the repetition? Let's just say in this example, S1 equals S2 equals 6. So the guess is K1 e to the minus 6t. That's one of them. Or in this case, yeah, put a minus 6 over here so it's more realistic. But the second term, we can't guess K1 or K2 e to the minus 6t. We put a T multiplier in. And that's why we wrote this way. K1 plus K2t e to the minus 6t. So what we did is we took this form, there it is, and we multiplied it by t. So we get a T multiplier. Anytime something happens that is repetitive, we put this T multiplier in. So now let's see how this pertains to the homogeneous response and the forced response. So let's look at this example. Consider the following example. X double prime plus 3x prime plus 2x equals 5 e to the minus t. So right now, I want to go right to the forced response. Anybody tell me what I should guess for the forced response based on this equation and what we have taught you in this course so far? What should my guess be?
AE to the AT.
AE to the what t?
AT.
Okay, but what's the value of A? I'm going to point to it right there. See it?
0 or
Nope.
-1. I'm sorry.
-1. A. So it looks exactly like this. So just remember that. It looks exactly like this, except we ignore the constant and we put our own constant in and we call it A. Excellent. So when I do that, following along, I need XF double prime. And if you followed along, that should be -1 A e to the minus t. And then XF double prime equals another minus, makes it a positive, A e to the minus t. All right. Now let's see what happens. We're going to plug this in and we're going to solve for A, correct? That's what we need to do. Plug it in, solve for A. So here we go. X double prime, A, e to the minus t, plus 3x prime, minus A, e to the minus t, plus 2 times x, A, e to the minus t. So this one, that's that one. This one, that's that one. This one, that's that one. And all of that should be equal to 5 e to the minus t. So we say, oh, e to the minus t, e to the minus t, e to the minus t. Let's factor it out. So we will. There's my e to the minus t. And let's see what we have. We have a minus 3a plus 2a. Look at this. 0 e to the minus t is equal to 5 e to the minus t. And all of you know that this cannot possibly be true. So one of two things happened. One, you made a math mistake. Check your math. We didn't. Two, your guess is wrong. And we are in this latter situation. Your guess is wrong. And the reason your guess is wrong is because this here is going to look exactly like a term that is in the natural response. Because we know when we put in a natural response, we know we put it in this equation, it's going to be equal to 0. It satisfies the homogeneous equation. So let's take a look at that natural response. All right, let's go back to the equation. Let's copy this equation down over here. X double prime plus 3x prime plus 2x equals 0. So that is the homogeneous equation. S squared plus 3s plus 2 equals 0. S plus 2, s plus 1 equals 0. S equals minus 2 and minus 1. Therefore, X homogeneous equals K1 e to the minus 2t plus K2 e to the minus t, or minus 1t. There it is, that term. That is a homogeneous, a term in the homogeneous response. So we know it satisfies the homogeneous equation. So we know when we plug it in, we're going to get 0. And that's exactly what we did. We guessed a e to the minus t. And when we plugged it in, we got 0. Sorry, 0 here, that's 0. So we got that 0. So we knew that. This is why we always do our homogeneous response first. And now, once we've done the homogeneous response, we look down here. Here's the homogeneous response. Then when we say, okay, we should guess this, up here, we're going to immediately compare this to each of the terms here. And we say, oh gosh, no, that's already down here. I can't guess that. So here's what we do. So instead, we guess that XF is equal to A T multiplier T e to the minus T. So we just change it by putting in an added T multiplier. XF prime. Now this is the quotient rule. So it's the derivative of the first function, that's 1 times the second function, e to the minus t, plus the first, t times the derivative of the second function, minus e to the minus t. Grouping that all together, all of this is equal to a, here's a minus t here and a 1, so then I have 1 minus t all times e to the minus t. And I encourage you to leave it in this form, in the form where group all of this together and then multiply it by just e to the minus t. The reason I recommend you do that is because we need to take another derivative. And so this is going to work real well when we're using the product rule again. So let's take the derivative again. Notice the a, it stays out front. The derivative of the first, minus 1, times the second, e to the minus t, plus the first, 1 minus t, times the derivative of the second, minus e to the minus t. Clean this one up. Equals a. Now, I have done this minus 1 that I have here multiplies each of those terms there. So that's going to give me a negative 1. I'm going to pull this out, make that plus, make that minus, make that plus. And now I have a minus 1 here. I have a minus 1 here. That's going to give me minus 2. And I still have a plus t. And that's all times e to the minus t. Now we have our 3 terms. So now we're going to put it into the differential equation. So as a reminder, the differential equation looked like x double prime plus 3x prime plus 2x. And all that from the beginning was 5. If you remember, it was 5 e to the minus t way back here. 5 e to the minus t. So that equals 5 e to the minus t. Now just slide this down. So I have my 3 terms to substitute in. X double prime. A minus 2 plus t e to the minus t plus 3 times a 1 minus t e to the minus t plus 2 times a t e to the minus t. And all of that should be equal to, what's interesting is it's only equal to 5 e to the minus t. Even though the guess started with an extra t in it, all of it is going to be equal to 5 e to the minus t. Okay, so here's what I'm going to do first. I'm going to take all the terms in these parentheses that are constants, constant, and no constants in the last one. So I have minus 2a, that's this 2 times that, minus 2a. And then I have plus 3a, all that, plus 3a. And I have nothing else, so just those 2. And all of that multiplies e to the minus t. Then I'm going to take the other terms, plus, now the ones that multiply t, a times t. So all of this is going to be the terms that multiply t, e to the minus t. So from the first one, just a multiplies t, just a. And the second one, 3a and a minus sign. So minus 3a. And then the last one, 2a plus 2a. And check this out, it will always happen. All of those are equal to 0. A minus 3a plus 2a is 0. So there's nothing there, and all of this is equal to 5 e to the minus t. And all we're left with is this coefficient must be equal to this coefficient. So that tells us that minus 2a plus 3a is a equals 5. Woohoo! So therefore, x sub f, the forced response, is 5t e to the minus t. I'm just putting 5 in for a. Slide back. There's a right there. Just putting 5 in for a. So we solve for a. There it is. X sub f is 5t e to the minus t. And there's our solution. What other term could have been, where's my differential equation? What other kind of a term could have been here in this differential equation and would have caused me a problem? Tell me give me an example of another term that could have been there that would have been a problem. What other term could have been a problem? Different than an e to the minus t term. Hint, what else will be excitation at a natural frequency? What else is in the natural response? What else is in the natural response? So if this equation, instead of having this, had something like 10 e to the minus 2t, that would be excitation at a natural frequency. And your guess would look like what? Somebody give me this one. I'm going to wait all day long and then make you read the book and understand all the other information I'm not covering in the rest of the lecture. What would your guess be?
AT e to the minus t.
That's exactly right. Appreciate that. AT e to the minus 2t. You just put in a t multiplier. So that is one special case that occurs, and it will occur from time to time. It is called excitation at natural frequency. If you care, for those of you who care, this is what's called resonance. When you do something and something resonates, you are exciting it at its natural frequency. You're putting in an input that is at a natural frequency of the circuit, and what wants to happen is this thing wants to kind of blow up. That's what's going on. Okay. We've got everything in place now, so finally we can get to the complete solution or the total response, depending upon how you like to word it. Complete solution or the total response. So what we're going to do now that we have the two terms, we will have the total response is X equals XH plus XF. That is the total response. So we're going to get each of them separately. We're going to now add them together. But the problem is what? Anybody see any problems right now? We're going to add these together. I'm going to do it for this particular example. Ready? So this is in our example. K1 e to the minus t plus K2 e to the minus 2t. I know I wrote them backwards. I wrote them the other way. It doesn't matter. Plus 5t e to the minus t. See any problems with that? Or do you feel warm and fuzzy? You love it. Done. Everything's done. Got it. I know it.
It's adding the K1 and the K2 with the...
Yeah. I mean, how many of our responses have unknowns in them? Can you imagine developing a circuit, creating a circuit, building it, designing it, and then, well, I don't know, you might get this response, you might get another one. I'm not really sure what you'll get. We know exactly what we're going to get. And so, unfortunately, K1 and K2 are still unknown. Just because we added them together doesn't mean we have their values. So to solve for K1 and K2, the way we're going to solve for K1 and K2 we need two initial conditions. The problem is the initial conditions we are either given or that we can find very easily are not the two that we need. So the two initial conditions that we can get pretty easily are the currents through the inductors and the voltages across the capacitors. But I need two conditions about X. We need two conditions for X. In our case, it'll be for I, or for V, or for V1, or for Vx, or for IA, or IB, et cetera, et cetera, et cetera, right? Whatever the variable is in our differential equation, that's the variable. We need two initial conditions for that one. So one of them is going to be pretty easy to get. One of them, so usually this is what we rely on. Usually we rely on initial conditions at time t is equal to 0 or 0 plus, or t equals 0 plus, depending if there's a switch in the circuit or not. A lot of these circuits are so hard, we don't even put switches in there because, God, you'll have 90,000 things that you have to work on in one circuit. we're going to do one circuits problem. We might start it today, but we'll do one circuit problem. And man, it is going to be a nightmare. All the work that needs to be done. So if there's a switch, we use 0 plus. If there's no switch, we'll use T equals 0. The second condition we should be able to find from one of the circuit equations that we wrote. And I just want you to write this down. So we need two initial conditions. So let me tell you what the two are that we're going to look at that are almost going to work for us almost exclusively. So those two conditions are going to be the following. We're going to look at X at 0 or 0 plus. I'll put a plus in there just in case. And the other condition is the derivative of X evaluated at T is equal to 0 plus, which some people write this way. Okay, some people write it that way. Another way you can write it, X prime at 0 plus. All of those. So this and this and this, they're all equal. They're the same thing. So this one is new to us. We haven't been looking for derivatives at 0 plus, even though I did show you how you could do that. And so generally, we'll be able to find that information from the circuit, or it's given to us. So let's start with an equation that we have where it's given to us, and then we'll work our way to some things that are a little more difficult. So here's an example. V double prime plus 3V prime plus 2V. So half of you are saying, thank God we finally have voltages. And the other half of you are saying, man, I like the world of math. Please use X's. So V double prime plus 3V prime plus 2V equals 4T. Let's just pretend that's what we figured out from our differential equation. And you are also given V at time 0 is equal to 1. So there's no switch here. So V at time 0 is equal to 1. And V prime at 0 is equal to 5. All right, so you're given the information. Find the complete solution for V. All right. We didn't even get this from the circuit. I gave you that. Finding this from the circuit right there can be sometimes impossible. Even for a second order circuit can be really, really hard. I will only give you circuits that are much easier, and I will show you ways that you can do that that will help you find that as easy as possible. All right, so this is our problem. Somebody tell me the first step that I should take. So we'll break this down into steps. Step 1, what's the first thing that I should do?
And the homogeneous solution.
Okay, excellent. So we're going to find the homogeneous solution. And so V sub H is going to be found by writing what? Do we need to write the homogeneous equation, or can we just go right to something else?
Characteristic equation.
Yeah, we're going to go right to the characteristic equation. Here we go. S squared plus 3S plus 2 equals 0. We just saw this in the example I just did. S plus 2, S plus 1 equals 0. So S1 and S2 are equal to minus 2 and minus 1. Notice it doesn't matter which one is S1 and which one is S2. It doesn't matter. You call them whatever you want to. K1 and K2. It doesn't matter which one's K1 and what's K2. But whatever you decide K1 goes with at the beginning, it needs to stay there through to the end. So here we go. This is, again, category 1. So the not X. Gosh, I'm so used to doing X's with you, I forgot that we're now working in the world of voltages. So V sub H is equal to, I'm going to do K1 e to the minus 2t plus K2 e to the minus t. So that's the first thing we do, I'm going to hold that, and I'll put that in the box. And your tendency is going to want to be to find these constants immediately. But you're going to find out you have to do all the dirty work first, and then we're gonna go in and find the constant at the end, or the constants, two of them, K1 and K2. All right, next step.
Find the forced response.
Find the forced response. So we're going to guess V sub F is equal to what? What's our guess?
AT plus B.
Outstanding, Jack. AT plus B. So we need VF prime, which is A, and VF double prime, which is 0. And we're going to substitute those into the differential equation. I will continue to write the differential equation over so you can continue to see it. So here we go. Whoop. I didn't like that. Excuse me while I'll put this to voicemail. Okay, and now I've got to find out what the heck just happened here. All right. Back up, back up, back up. Good. Open that up. Okay. Great. Okay, so the differential equation is V double prime plus 3V prime. Somebody needs me bad, they're just gonna have to wait. Plus 3V prime plus 2V is equal to 4T. So now we're gonna substitute these in. So V double prime is 0. 3 times V prime, but V prime is A, plus 2. Hey, Keith Johnson? Yeah. Could you do me a favor, please? Excuse me for one moment. Kevin Steele tried my phone and then my cell phone. Could you? Yeah. Thank you. In the office or home? That was his cell phone. He's at home. Thank you. And then AT plus B is the forced response. And that's equal to 4T. So I have 3A plus 2B. Those are the constants. Notice always group like terms. Plus 2AT equals, over here, a reminder, 4T plus 0. So this is the constant. And over here on this side, this is the constant. So that says to us 3A plus 2B is equal to 0. The other equation is this multiplies T and this multiplies T. So we're always, with the forced response, we're always comparing like terms on both sides of the equation. If there's no term over on the right-hand side of the equation, it means the coefficient is 0. So don't ever forget that. It just means the coefficient is 0. There's a constant over here. There was no constant over here. There's nothing. So the constant is 0. So that's one equation. The second equation is 2A is equal to 4. Well, we can solve that one immediately. A equals 2. Now I'll use that and I'll put it in here. And when A is equal to 2, I have 3 times 2 plus 2 times B is equal to 0. Solve for that. 2B equals minus 6, B equals minus 3. So now we have A, now we have B. We're going to put both of those into our guess. So that tells us that VF is equal to A is 2, times T, plus B, minus 3. So let's just make this a straight minus 3. And there's that part. So now we have both of them. Next step is take those two terms and put them together. Okay, so we're going to put those together to form the complete solution. So here we go. Step 3, the complete solution is V equals VF plus VH. And that's equal to, well, VF, 2T minus 3, plus VH. And VH is K1 e to the minus 2T plus K2 e to the minus t. I want to double check and make sure I didn't switch my k's around. K1 e to the minus 2t. Good, I did not. So that's the whole solution. So now we feel like, oh, we've got the whole solution. It feels like we're done, but we're not, because we still have K1 and we still have K2. So now we take this whole solution, and now what we do is the following. So that's the total response. So step 4 is use the initial conditions. To find the K's. So they are in there until the last step. The values of K1 and K2. All right, and this is how it works. And I would recommend that you follow this the way I do it. So the first thing I do is I write this. So V at 0. On this side over here, V at 0, on the left-hand side of V at 0, I'm going to put in there the value that was given to us. And that value was 1, I believe. Just double check that number. V at 0, V at 0, V at 0 is 1. So I start there, and underneath it, I write this. I write V prime at 0, and that was given to us as 5. Then what I do on this side, on all the way on the right, is I use this V here, and I evaluate by plugging in t is equal to 0. So here we go. 2 times 0 minus 3 plus, we all know when we put 0 in for the exponent, all of that exponential is just 1. And that exponential is just 1. So it's going to be plus K1 plus K2. So this first equation looks like the following. K1 plus K2 equals, that's 0. I'm going to take my minus 3, bring it over to the other side, and that's going to be equal to 4. So that's my first equation. K1 plus K2 is equal to 4. Now, this is where students make a mistake. They look at V of 0 and they say, oh, I have V of 0 is equal to 1, and I'm going to take the derivative of that. So what we have to do is we have to take, whoop, don't move that. We have to take the derivative of this function. This is the V function. Take the derivative first, then substitute in 0. So the derivative of that function, 2, so the derivative of 2t is 2, the derivative of minus 3 is 0, plus, and now the derivative of these terms, minus 2k1 e to the minus 2t, and then we're going to set t is equal to 0. And then plus, this is going to be a minus k2 times e to the minus t, and then we're going to set t is equal to 0. So you can see when we set t is equal to 0, again, this is 1, this is 1. So what we have on this second line is 5 equals v prime at 0, but v prime at 0 is equal to, from the equation, is 2 minus 2k1 minus k2. So the second equation that we have is our first equation for k1 and k2. The second equation is minus 2k1 minus k2 is equal to, bring this to the other side, is equal to 3. How do I solve those two equations? Whichever way is easiest. So this is what I see that's easiest this time. Add them. When you add them, those cancel out. And when you add, you get minus K1 equals 7. So therefore, K1 equals minus 7. Take that, I'm going to plug that in here. If K1 is minus 7, you can see that K2 must be equal to 11. All right, are you ready? Here comes the home run. We're going to put it all together. So V equals minus 7 e to the minus 2t. That was K1. Plus 11 e to the minus t. That was K2. Plus 2t minus 3. And assuming this is a voltage, it is in volts, then that is the complete solution. How'd you like that? Comments or questions on that entire process? Everybody's good with that? You understand that process? So let's try to write out the steps for this process and what we're doing. So to solve second order circuits. Some of these you don't have to do in this order, but I'm going to sort of recommend that you sort of look at this order of doing things, because I think it'll make your life a little bit easier. Step 1. Write your circuit equations. Mesh or nodes. And you're going to try to do this, hopefully, in terms of, and there are times when you don't have to do this, in terms of the variable you're trying to solve for. So you have to think thoroughly through this. I'm going to show you an example up above here. Pretend this is a resistor. Pretend that's the current I. Pretend that's the voltage V. If I asked you for the voltage V, you could solve for I, because you know once you have the answer for I, V is nothing more than I times R. That's simple. You can do that. Okay? So when you have circuit elements, you don't actually have to write your equations in terms of the variable you're asked to solve for, as long as you know how to get there easily. So we can solve for I, and then we can get V. We can solve for V, but then we can easily find I. So be smart about that. So write your circuit equation in terms of the variable you're trying to solve for. Then, after we do that, what we're going to do is we're going to try to combine your circuit equations. This is one of the hard parts. It's new. In a way that will allow you to develop a second order differential equation in terms of the variable you're trying to solve for. So you have to do this combination and combining, and I'll show you how that's done with an example. It doesn't make it easy, but I'll show you how it's done with an example. In fact, this step usually causes you to do combining of equations in a manner that is backwards of what you will think. It's going to be backwards of what you will think. All right. So then, once we've done that, as long as you're in circuits world, what you might want to do is find your two initial conditions. And hopefully they are either given or you can find them, or one of them, from your circuits equations that you wrote in step 1. Okay? So usually when we're looking for, particularly in this case, usually we're looking for, oh my gosh, how do I find V prime? How do I find that at 0? And the answer is, this is what you're going to find. You'll find a way to get this from your circuit equation, from one of your circuit equations. That's what we're going to show you how to do that. All right, so that's all the setup. Now, step 4, let's start solving. Find the homogeneous solution to your equation. I'm going to remind you, this will involve a K1 and a K2. This involves K1 and K2. So they're going to be in there. You cannot get rid of those until the very end. Stop moving. These things are moving on me. Okay. So you've solved the homogeneous equation. There's steps A, B, C, D just in that alone. Then find the forced response. Just as a reminder, this is completely known. No unknown constants. Step 6, form the complete solution. And I'll write it this way. X equals XF plus XH, right? We know it's the sum of the homogeneous response and the forced response. So we form the complete solution. Reminder, there are still 2 unknown constants, 2 unknown values. They are K1 and K2. Okay, so we still have unknown constants. That's step 6, and we still don't know certain values. Step 7 is what I would do is, once you form the complete solution, compute x prime, the derivative of the complete solution. So compute that derivative. Then 8, use 6 and 7 and the initial conditions to solve for K1 and K2. 9, substitute them back into the complete solution, and you're done. Okay, here's step 10. Probably the most important. Reward yourself and go get an ice cream. This is a long process. It is a challenging process. And when you make it through the end, you go, oh my God, that was unbelievable. That was really cool. Okay, let me stop sharing my screen and then chime in with you over here. So we've got a big, large process to be able to solve for these answers to these second order differential equations that come from second order circuits. But the toughest part is not solving the differential equation. Make that be the easiest part of solving this problem. We've gone through, we've outlined the steps for how to do that. Yes, there are multiple sub-steps in each of those, but we've outlined those steps for doing that. So that's not too difficult. The challenging part, excuse me, the challenging part is actually getting the circuits equations. And once we have the circuits equations, it's manipulating them in a manner that's easy. There are some circuits where that will be really, really easy, and there's some where it will be really, really hard. And when we talk the next time, I'm going to try to give you some tips on different things to do when you have a circuit that can make your life a little bit easier. For example, picking the right variables to write your circuits equation can help you in a big way. And then knowing how to use those variables to find what it is that you're after is going to be important. So we'll see how to do all of that the next time we're together next week. So all of you, stay safe, stay away from other people, right? Continue to be cognizant of the coronavirus and the challenges that are out there. I think I have papers from all of you except Garrison. I'm not sure if I saw your paper today come through. Please make sure your paper is submitted today. That was the due date. On Monday, we'll talk about what we might think about with regard to the oral presentation and when we want to do the oral presentation and how we'll do the oral presentations. That'll be a nice little bit of a relief from getting a lecture with me writing on a white pad in my office. So we'll talk about that. The homework assignment, several of you turned in homework. It wasn't due today. Let's make those, that's the complex number assignment. Let's make that due next Friday. It won't take you anywhere near as long as circuits problems. It's much easier. So I may have another assignment that I'll give you on Monday that may also be due on Friday. So things are kind of weird right now, obviously, with the way we're operating. So we'll just see how things are going as they're going. Any comments or questions that anybody has for me before we part ways for the weekend? Please give me feedback. Is this working for you? Are you absorbing the material? I know it's a little different than being in class. Are your connections good enough that you're getting it, you're understanding the material? Or is it like, you know what, you move that whiteboard too fast, I keep getting glitches, my internet is not good quality internet, and I'm having a difficult time. How is this working for you on your end? Because it's working okay for me.
Yeah, it's working good on my end.
Okay, thank you, Jack. Appreciate that.
Me too.
Great, thank you, Jordan. Appreciate that. So I am recording these. I missed the recording on Tuesday. I have placed 2 of the recordings on YouTube already. Arushi, I'm going to try to take all of my white pads that I have here, and I'm going to try to send them to all of you so that you have them, or upload them in Blackboard. I'll see which one works easiest with regard to transitioning it from the white pad. So I'm going to take a look at that today and see what I can do with that. If there are no other comments, have a great weekend. Again, stay safe, and I'll look forward to seeing you sometime on Monday. We can talk on Monday again about oral presentations, quizzes. Right now, I didn't give any quiz this week. I've had some recommendations from some other faculty about ways to do quizzes, but they're not in the same world that we're in, where you're physically writing information down and drawing a circuit and writing things in your diagram. It's a little bit different. So it doesn't work out quite as well as they think it would. So we'll see what I can come up with for that. And by the same token, if any of you has an idea about ways to take quizzes, we can talk about that as well. I think if all of you have ready access to be able to scan something and send it to me, we could do quizzes with me just having you have your video on. I can see that you're sitting down taking the quiz, and then when you're done, you send it right off to me. So that's one thing that could work, but we can talk about that sometime next week. Have a great weekend and stay safe, all of you. Okay, take care.